Hello, welcome back to my channel. This is Kai Salsu, the previously mentioned electrical and electronics engineer. I'm about to create the second video of the Physics 111 Introduction to Physics playlist. This video is going to be about the unit vector, how vector multiplications happen, and a continuation from the initial topic of scalars, vectors, and polar and Cardassian coordinates. I'm going to switch to on-screen recording. Hopefully you will be able to hear my commentary this time. If you don't, then we will have to fix it, but most probably you're going to be able to hear it. So as previously mentioned, I have asked ChatGPT to provide explanations. Now, since I have undertaken these courses myself previously, if ChatGPT ends up making mistakes, I will be able to catch it. And when that becomes the issue, I will of course mention it and pause the screen based on the situation. So ChatGPT has provided unit vectors, definition and properties. The definition: a unit vector is a vector of length magnitude 1 that indicates direction only. So a unit vector involves only the direction. Now here's the catch: when the direction is mentioned of magnitude 1, what we are assuming is the magnitude remains 1, the direction is the part that remains to be discussed later on. Notation: commonly written with U notation or as basis vectors I, J, K in Cardassian coordinates. You know how we have X, Y coordinates in the two-dimensional plane? You can also express a three-dimensional plane using the Z axis. The same thing can be translated into I, J and K axes when you are thinking about vectors and their three dimensions. Now here's an example of a unit vector. The unit vector is I1, 0, 0, J0, 1, 0, K0, 0, 1. So what it basically means is that it has a magnitude of 1 in the I-axis, a magnitude of 1 in the J-axis, and a magnitude of 1 in the K-axis. You have to understand and notice that in each of the arrays, the corresponding other two options remain null or 0. What that basically means is that this unit vector is nothing more than coordinates being represented of a point at x equals to 1, y equals to 1 and z equals to 1 from a point of origin where x equals to 0, y equals to 0 and j equals to 0. The properties are: the modulus of unit vector is always 1, which means it can never be negative. So a unit vector is nothing more than an idealized state of vectors where the negative does not really exist. It has to be positive. It has to be positive in all three axes. Multiplying a unit vector by a scalar A scales its magnitude. A unit has magnitude A modulus. What that basically means is that if you scale a unit vector by any number, what you're basically doing is you're multiplying it. So 5u notation basically translates to a 5-time magnification or amplification of the unit vector. Unit vectors show direction. To get a unit vector from any non-zero vector v, normalize it. Okay, so unit vectors show direction. and to get a unit vector from any non-zero vector v. So for example, let's say you are trying to extract the direction of any non-zero vector. What you need to do is you need to divide that vector by the modulus of that vector. So what you're doing is you're cancelling out the negative. Once you cancel out the negative, what you do is you find the magnitude of the direction. Basic unit vectors are orthonormal. Okay, orthonormal is a term that we are going to explain, and I'm going to refer to Google to explain what orthonormal means. So here is something that I have developed while being a researcher, is that I always like to use sources in order to provide explanations, because I'm being honest, none of these concepts were created by me. I am nothing more than a parrot. Well, I'm a little bit more than a parrot in the sense that I've actually learned these, applied, and successfully achieved marks, solved problems, and passed examinations. That's the only difference between a parrot talking about unit vectors and myself. But anyway, moving forward, orthonormal. Orthonormal is a term describing a set of vectors that are both orthogonal, perpendicular to each other, and normalized. Okay, so orthonormal has two components. The first component is that it needs to be orthogonal or it needs to be perpendicular, and the second component is normalized. Perpendicular is very simple. It needs to be at 90 degrees, okay, with an adjacent value or a figure. Normalized is something that we're going to get into the explanation of. Each vector is a unit vector with a length of 1. This means the dot product of any two different vectors is 0, and the dot product of any vector with itself is 1. A set of orthonormal vectors is also linearly independent and is shown as an orthonormal basis of the vector space, simplifying many linear algebra calculations. Key characteristics of orthogonal are: the vectors are all perpendicular to one another, which means the vectors are at 90 degrees. So for example, the x component is 90 degrees with the y component, and the z component is 90 degrees with both the x and the y component. So that is what orthogonal means. The dot product of any two different vectors in the set is 0. ui uj equals to 0 when I is not equals to j. So if you multiply, it becomes 0. Normalized. Every vector in the set is a unit vector, meaning it has a length or magnitude of 1. The dot product of a vector with itself is 1. ui dot uj dot ui equals to 1. So if you multiply the x component of the vector with itself, it is going to be 1. Linearly independent. Because the vectors are orthogonal, they are also linearly independent. What that basically means is that there is no linear relationship between the two. They are at 90 degrees with each other. How to create an orthonormal set? We are not going to get into this. We are going to move back to unit vectors. Example, basis unit vectors are orthonormal. I dot j equals to 0, which means if you multiply any two orthogonal parts of the unit vector, the resultant is going to be 0. If you multiply any axis of the vector with itself, the multiplication is going to be 1. Example, orthogonal plus unit length. Example of normalization, 2D. Let v or vector equal to 3 and 4. The 3 and 4 are nothing more than the numerical values of I and j. Magnitude modulus v equals to square root of 3 square plus 4 square equals to root over 9 plus 16 equals to root over 25 equals to 5. So what you are doing is you are doing nothing more than Pythagoras theorem. This is Pythagoras theorem. You are using Pythagoras theorem to find the modulus magnitude of a two-dimensional unit vector. This is class 5 mathematics. Unit vector v equals to 1/5 3, 4 equals to 3 by 5, 4 by 5. Check magnitude. So in this part, what you're doing is you're dividing it by 5. Why are you dividing it by 5? You are dividing it by 5 because 5 is the magnitude. So if you divide or multiply the unit vector by itself, the answer should be 1. So that was previously discussed. Now this is a proof of that. So when you square root of 3 by 5 whole square plus 4 by 5 whole square, it becomes 9 by 25 plus 16 by 25, which is nothing more than partial fractions adding up to create 25 by 25 square root equals to 1. Part 2, components of vectors. Definition. A component is the projection of a vector along a coordinate axis or some chosen direction. In Cartesian coordinates, a vector is represented by its components. Previously mentioned Cartesian and polar coordinates. In Cartesian coordinates, you have I and j values. In polar coordinates, you have r values and cos theta values. 2D Cartesian, v equals to vx, vy equals to vxi plus vyj. So the I and j are nothing more than the x and y component. Vx is the x component, Vy is the y component. 3D Cartesians, V equals to Vx, Vy, Vz. So the difference between the 3D Cartesian and the 2D Cartesian is that there is an additional axis added to it, which is nothing more than the z axis. And we have added k as an alternative to it. So Vx, Vy and Vz becomes Vxi plus Vyj plus Vzk. Finding components from magnitude and angle. Now this becomes interesting because what you're doing is you're applying your previous knowledge from the first video where we talked about the relationship between Cartesian coordinates and polar coordinates, and you're using them to find components. Okay, so this is an example. If V has a magnitude capital V and makes angle theta with positive x-axis, Vx equals to V cos theta, Yx is equals to V sin theta. So what is happening is you have divided the Cartesian coordinates into its trigonometric components and have added trigonometric ratios to create two separate expressions, V cos theta and V sin theta. Example, components from magnitude or angle, colon, V has magnitude 10 and angle theta equals to 30 degree. Compute components. So now we have an example where we have a given magnitude and a given angle theta. Compute components. Vx is equals to 10 cos 30 equals to root 3 by 2 or approximately equals to 0.86600254. What you have basically done is you have multiplied or you have computed the values of V as 10, the values of theta as 30, and you have multiplied it with cos 30. Why have you multiplied it cos 30? Because what you are doing is you have created, wait, I think it has made a mistake here. I think it should just be 10 cos 30. Let me check. This is why ChatGPT is not reliable. ChatGPT is not reliable is because ChatGPT adds random things based on its whims and wishes. (10 cos 30). Yes, 8.66 multiplied by cos 30. Wait. Yes, 8.66. The additional cos 30 that they have added here is redundant. See, this is why humans are irreplaceable even today. ChatGPT, as popular as it may be and as sophisticated as it may be, it fails in basic mathematics. You need mathematicians. Learn mathematics. Anyway, moving forward. Example, components from endpoints. Vector from A to B. Point A 1, 2, B 4, 7, vector AB equals to B minus A. 4 minus 1 comma 7 minus 2. So what you're doing is you're subtracting the respective values of x and y in each specific box, and you're computing the values of vector or the difference between b and a. Algebraic presentation of vector sums. Vector addition component wise. Vector addition is pretty simple. What you do is you take the individual x components and the y components and you add them and you find these values. I'm going to recite it anyway. Ax comma ay comma az equals to a, and b equals to bx comma by comma bz. A plus b equals to ax plus bx comma ay plus by comma az plus bz. Same for 2D. Add the x components and y components separately. Geometric view. Place tail of b at head of a and resultant a plus b runs from start of a to the end of b. Parallelogram law is another visualization. Scalar multiplication distributes over addition. So when you are multiplying c to both a and b, what happens is you get scaled versions of both a and b. Example 2D numeric vector sum. Let a equals to 2 comma minus 1, b equals to minus 3 4. Add components a plus b equals to 2 plus minus 3 comma minus 1 plus 4 equals to minus 1 comma 3. Magnitude of resultant a plus b modulus equals to root over minus 1 whole square plus 3 square equals to root over 1 plus 9 equals to root over 10. Example 3D numeric vector sum. U equals to 1 comma 2 comma 3. V equals to 4 comma minus 1 comma 2. U plus V equals to 1 plus 4. You're adding the x components. 2 plus minus 1. You're adding the y components. And 3 plus 2. You're adding the z components. And you get 5 comma 1 comma 5. Putting it together, compute sums using unit vectors. Write vectors using unit basis. A equals to axi plus ayj plus azk. So you are multiplying the unit vectors to their specific components, and you are getting two different unit vectors for a and b, where b equals to bxi, byz, byj and bzk. Then a plus b equals to ax plus bxi plus ay plus byj plus az plus bzk. Example, combine normalization and sum. Given p equals to 3 comma 4 and q equals to minus 1 comma 2. Normalize p colon modulus of p equals to 5, p equals to 3 by 5 comma 4 by 5. Compute 2p plus q. So this is a little bit complicated compared to the first one. You have to multiply p with 2 and add q. So what you do is you first multiply 2, the unit vector of p, so that gives you 6 by 5 comma 8 by 5, and then you add q to that and you get as decimals 0.2 comma 3.6. Extra useful formulas, quick reference. Magnitude 2D or 3D hole x comma y modulus equals to square root of x square plus y square. X comma y comma z equals to root over x square plus y square plus z square. This is nothing more than what you learned back in high school in order to find the value of tangent of a three-dimensional cuboid. Whenever you are thinking about vectors or matrices or thinking in terms of 3 dimensions, you have to understand that this is nothing more than a layer added on top of what you already learned in mensuration back in the 7th or 8th grade. Short work summary, example end-to-end. Problem: a force F has magnitude 20 Newton at 120 degrees from positive x-axis 2D. Another force G equals to 5 comma minus 3 N. Find resultant R equals to F plus G and its magnitude. Steps: components of F. F of x 20 cos 120. See, again it has multiplied cos 120 another time, and that is useless. Equals to cos 180 minus 60 equals to minus cos 60 equals to minus 0.5. So f of x is equals to 20 into minus 0.5 is equals to minus 10. So what it has done, it has used the principal component or the resultant force and it has multiplied it with cos to get the x component and y component by multiplying the sine ratio, and it has gotten f
as a vector which is expressed as approximately minus 10 comma 7.3205. At g is equals to 5 comma minus 3. Why is g 5 comma minus 3? Because g is already expressed as 5 comma minus 3. R equals to minus 10 plus 5, you are adding the x components which results in minus 5, and you are adding the y components 17.3205 plus minus 3 which is 14.3205. Magnitude R modulus equals to square root over minus 5 whole square plus 14.3205 whole square equals to root over 25 plus 205.0619 equals to square root 230 minus 0.0619 equals to 15.167. Final tips: always keep track of components XYZ for algebraic work. It is the simplest and least error prone method. Use vectors I, J, K for neat symbolic expressions. Normalize when you need directions only. Example, direction cosines, unit force direction for non-Cartesian bases. Always remember the difference between Cartesian and polar coordinates. If it is polar, then it has a theta attached to it. If it is Cartesian, then what is happening is it has axis values or axis components. Project comma projection dot product is how you find components along arbitrary directions. If you want, I can give, okay, so this is ChatGPT trying to provide a lot of other things which are currently unnecessary. This concludes the entirety of the lecture titled Unit Vectors and Their Properties, Components of Vectors, and Algebraic Presentation of Vector Sums. Please provide, okay, I don't have to repeat that. Anyway, that's it. So that concluded the lecture 2 of Introduction to Physics of Physics 111 course. I apologize early and I thank you for your patience because I said I would deliver these videos in 2 to 3 days, but it is obviously taking longer. I will try to upload a few more videos tomorrow. Be patient and like, share and subscribe if you're liking what I'm doing, and let me know in the comment section if you think I should not use ChatGPT, because honestly speaking, I have to do a lot of things on a daily basis and I'm actually not getting paid to do any of this, and ChatGPT just makes things simpler, and which is why I like ChatGPT. A lot of people don't like ChatGPT. I like ChatGPT because ChatGPT is like an assistant who ends up creating a rough framework for what I want to express, but then ultimately I have to be the decision maker. I'll expand more on this in the artificial intelligence playlist. Anyway, see you soon.